So your question about the zero annihilator thing?
I don't know why I forgot about that. Yeah, of course, I might say all this.
That was the module we used, right?
Right.
Why does it have zero annihilator?
Because
It's got one in it, right? So if there's something in T that annihilates this module, it has to annihilate one, right?
zero.
What's that?
That's
Right. That anything that kills this module has to kill every one of these, right? In particular, it has to kill one. So if T times one is zero, then T is zero.
okay. Oh yeah, heard it.
You want a logic class? Sorry, not here. Okay, so here's now that we've reduced this integrality. Well, I shouldn't say reduced it, but if you have the notion of an integral element, then you can think of this in terms of, can you find a finitely generated module such that UA is contained in A? This makes the following theorem a lot easier. But R and T be an extension of rings. If S and T are integral over R, then so R, number one, S plus T into ST. Now, before I prove this, let me sort of underscore, I think, really the value of this theorem. Same the elements. Let me underscore to you all that this is actually an easy example in a certain sense, right? Because would everybody agree that both of these elements are elements of T that are integral over Z, right? Radical 2. There's a polynomial that's a root of coefficients. What about that? How about that? So let's jump on about this. Two, of course. What about that one right there? Actually, maybe I should do it with the other one because that's even worse, right? Well, this is it clear that this is a root of a monic polynomial with coefficients in Z? Well, I mean, if you played around with this, the Galois theory, then maybe it's like, well, yeah, it kind of seems like it, but it's not really clear, is it? Let's figure it out. And I think this is kind of an important part of the process. You can do this much more cleanly than I'm going to do it. You know a little bit of Galois theory, but I'm gonna get on the bulldozer and go. Doesn't that look right? 5 plus 2 radical 6, right? And you know what? I'm going to give the cube a miss because I see something here. If I look at x4, that's actually going to be 49 plus 20 radical 6, I guess. 25. Yeah. Now, just making this observation here, and again, this is why I say this example is easy. I don't really have to use the cube in there. It just makes things messier. I can use a little bit of linear algebra, and I notice that if I have minus 10 times x squared plus x4, what happens here? Well, that's going to be minus 1, right? 3. And this translates into the desired polynomial. There you go. So it is root. But look, we got quadratics, we've got a quartic here, and it's not really clear. And also, I got super lucky, right? And of course, you might go back, just if you're masochistic, and replace that 2 by 3, like I erroneously wrote up here in the first place, and see what you get. This theorem says that yes, indeed, even if this were the cube root of 3 and the square root of 2, there should be some monic polynomial, probably of degree 6, if I remember any in algebra, it's worth, right? So this is an important theorem, right? Now, as I hope I illustrated in this example, doing a proof where we write this down here, or write a polynomial for this, is borderline hopeless. So notice that. Let's see here. Notice that since R is, or since T is in RT is a finite generated R model. In fact, it is generated over R by, and this is just how the proof works. Thank you for that. This is shown in the proof. This is a model. It's generated over R by T n minus 1, where minimal monic polynomial for T is of degree n. And it's that monic polynomial that does things for you, right? Because why do you only need these first? Why do you need only up to the n minus 1 power? Because the nth power can be expressed as a linear combination of these received by induction. So, what we want to do is, in particular, now that I've observed that, let me just state this in terms of the general theorem. So, as T(S) are integral, find finitely generated modules, I'll call them A and B. Such that SA is an A and TB is an B. Now note AB, and of course these are finite submodules of T, right? note that AB is also finitely generated. Because all you have to do is take all the generators A, maybe there's N of them, all the generators B, maybe there's M of them, and multiply together, and those two product generators generate all that. And of course, the product of the AI and BI makes sense. And so you can, of course, also arrange it so one is in here. Notice that S plus T, AB, AB, and ST, AB, AB. So S plus T and ST are A. Just like that. And see, that shows you the value of this approach because no polynomials to deal with. In fact, in a certain sense, you might think of this finitely generated module controlled by the polynomial for S and this finitely generated module controlled by the polynomial for T. And this is kind of the mixing up of the generators. Remember how with the example, we saw that we have, in fact, here my module might be generated by 1 in the square root of 2, 1 in the square root of 3, and in the product, we have this kind of larger module, and we got a 4th degree out of it. Okay, any questions on that?
So what was the point of what we wrote on the first board?
Oh, right here?
Yeah.
The point is I think it's important to, this is another good way to think about inequality, right? So this is just kind of the value to this is if T is integral, then RT is a finitely generated R module, and it also contains 1, right? And so I couched this more generally, but I could have used RT and RS, right? Okay. Here's a corollary that's very important. Corollary. Let R inside T be an extension of rings. Then I'm going to build this new ring, and I'm going to use the following notation. R bar sub T. This is the collection of T and T such that T is in this is a suburb of T containing R. This is called, often this is called the integral quotient of R. Okay, so why is this true? Notice that if R is an R, then X minus R X minus Y. So R again, because any element's integral over itself. So let's lay that down. So whatever this mess is, it contains R. By definition, it's contained in T. And so the only thing left remaining is to convince ourselves it's a ring. But notice if S, T, and R, then S plus T and ST are in that T. So RT false RT. This is really cool because it's not really clear at all. I think at the beginning that if I have two elements that are roots of a monic polynomial over some ring, that all these such elements will form a ring. It's not clear that it's closed under addition and multiplication. Let me give you sort of a definition here. So this is the terminology that I'll use. Definition. One, then R closure. Of R and T. If R is a domain for quotient field K, then sometimes its notation is, I want to be clear about this. I know that sometimes if you're talking about a field and you put a bar over it, that usually means the algebraic closure to the field. This means something. This is called the integral closure. This is a much more modest thing than an algebraic closure because it's everything that it's just integral, not algebraic, and your ceiling is the quotient field. It's everything in quotient field.
Question.
Yes.
In this definition and in the previous corollary, do we need to be concerned whether T is a overring or not, or does it not matter?
In my definition right here, all I assume is commutative ring with one. So maybe there's zero divisors. And even if it's a domain, T can be much bigger than being an overring, right? So you can have, for example, the integral closure of Z in the complex numbers, right? For example. Right. So what else did I want to add here? Okay. If R is equal to its integral closure, then we say R is integrally closed. And if T equals, that is to say, if every element of T is integral over R, then T is an integral extension. R. So examples here. So let me actually, before I do an example, let me throw in just kind of a fun result. And we've seen this. from example last time, we saw that any PID is infinitely closed. Well, that is part of it. Y'all remember that? What we did last time is we showed that that any element of the rational numbers that was integral over Z was already in Z. Right? And we noticed that our proof only required UFD. So if you have a UFD in its quotient field, anything that's integral over the UFD is already in the UFD. And so any UFD is integrally closed. Am I okay with that? So let's look at an example to spice this up. Um, uh, this is a polynomial ring where Dick Cheney shut up the linear time, right? So you've always got zero in front of your linear time here, right? So is this integrally closed? Can anybody see an example of an element that's in the quotient field that's integral over this? Okay, is it in the quotient field? Okay, notice. Oh, what? So notice that X, which is X, is in the quotient field. And X is a root of the polynomial t squared minus x squared. It's the root of a lot of things. T cubed minus x cubed, right? And so forth. So, observation one. F is not a anybody see bad factorization? Right, you could do this out explicitly. X6 x squared is an irreducible, x cubed is an irreducible. These are bad factorizations. And it's pretty easy to use a degree argument to verify that, in fact, in this ring, x squared and x cubed are irreducible. But it's kind of cool, right? Because I knew that a bad factorization had to exist going into it because it's not integrally closed. Right? Okay. What is the integrable closure of this?
must be bigger than closed and.
Well, right, so. That's right. So notice, let me justify this. Notice that X is in because we just showed that. Therefore, and of course, this thing here is contained in the zone interval. So you have X and you have all of this, and therefore f of X must be contained in the closure. Right? I definitely need that. Right. What about the other containment though? Right? On the other hand, suppose f of X is in the quotient field. By the way, the quotient field of this thing is rational functions of the field of variable X. Suppose is integral over integral over that. Notice that this is contained in f of X. Right? So if it's integral over this, it's integral over the bigger one, right? Because what this means is this thing is a root of some monic polynomial with coefficients here. Well, if it's got coefficients here, it's got coefficients here because that's a bigger ring, right? So f of X is integral over this, but this is a PID. So it's UFD. Therefore, f of X. Everybody okay with that? And I think it was you, Jared, that said this. So you observe that. All right. Okay, so you take this animal here, and its interval closure. Okay, in our example, we worked out is here, and the observation Jared made is this is a PID. So so you're stuck now because the interval closure of this is now X. You're always stuck after two steps. That's not obvious. But when we get to a theorem where I can make this more obvious than it is now. But I don't know. Can anybody see an obvious proof that if you take a ring, you look at its interval closure, now you look at its interval closure, that you get stuck after that first possible jump? I can't think of an obvious proof yet of what we've got, but we'll get something that will help us out in a bit. There's another question that I think probably should be asked at this juncture. We have a theorem that says that if you're a PID, even more generally a UFD, then you're integrally closed. What's the natural thing to ask? Is the converse true? That's a very natural thing to ask. Is it true? If you have an integrally closed ring, is it a UFD? Notice that this from by the way, what's the quotient field of this? Let's do this. I hope this doesn't turn out to be a disaster. I noticed that Q It's a quotient field. Okay. Now, let's suppose, and I'm going to make this easy on myself. I want to show if this is ever close, and then I'm going to ask you something about my approach. I want you to catch it. Suppose m plus n radical negative 5 over d is over this is what we kind of complicated. Right? By the way, here of course m and d. Right. Let me point out that a general element of this ring is fraction plus fraction times radical negative 5, right? What I've done here is hopefully made things a little bit more convenient on myself by making this a single denominator. Now suppose it's integral. So what does that mean?
There's some algebraic relation.
Okay. So suppose oh goodness, my life would be so much easier if I didn't have to deal with this, right? So what that means is, let's see, let's write this out. Let's write A equals A1 plus A2 radical negative 5, B equals B1 plus B2 radical negative 5. Okay. Now, I guess my goal was to show that D must divide both M and N, right? That's what I would really like to show. I want to show this as a close, right? Well, so let's try this. M plus N radical negative 5D squared plus A1 plus A2 radical negative 5 M plus N radical negative 5 over D plus D1 plus D2 radical negative 5 is equal to 0. Do I agree with that so far? Goodness gracious, what a mess. Any ideas what we might do here? Yeah, you know, it might make my life easier to get rid of that D, right, in the denominator. So let me multiply both sides by D squared. D there. Uh, I've really got my fingers crossed this moment, folks, but let me try to multiply this out and sort of group things together, right? So I'm gonna group all my radical negative fives together. I'm gonna group all my things that are integers together, and you better watch me. So I'm gonna get an n squared coming out of this, and I'm gonna get a minus 5 n squared, correct? And out of this, I'm going to get a 2nn. Y'all see what I'm doing here? Take the square, and then 2nn, radical negative 5 here. I'm going to get an a1n. Yes, thank you, a1nd. And yeah, I still need to be forgetting that d. And I get a minus 5 a2nd. And my mixed terms, if you will, are a1nd and a2md. And that's what comes out of that. So got everything out of that one. And finally, I get a d squared b1. And I get a plus d squared b2. And this whole thing is 0. This complex number is 0, right? So since this is 0, and 1 and radical negative 5 are linearly independent, I get m squared minus 5m squared plus a1md minus 5a2md plus d squared b1 is 0. And I get this other equation that 2mn plus a1md plus a2md plus d squared b2 is 0. Right. Are you okay with that? Where now? You
D divided m squared minus 5m squared.
okay. Right. So let's reduce this mod d, and notice that m squared minus 5 squared is equal to 0 mod d. And conveniently, right. So what that means is, so let's yeah, okay. That's line over here. So let's take this apart piece by piece. Notice, let's look at this system of equations. If D is an I prime, what happens? Okay. If D is an odd prime, then it's got to divide 2mn, right? But it can't divide 2 because it's odd. So it has to divide at least one of those. So we say D divides m without loss of generality. And what does the other equation now tell me? If D divides m, then D divides n. So D divides m unless D equals 5. Right? Because 5 complicates it. Right? Okay. What if What if, let's see, that means they put the even on. Well, on the other hand, what happens if D is 2? Yes.
I don't know if it really matters for the argument, but can we say assume D divides N without loss of generality, or are we just saying in the case that D divides N?
Yeah, actually, you're right, because it doesn't give, it bifurcates into cases that are not symmetric. So let me write this more carefully. If D divides M, then D divides N, or D is 5. If D divides N, then D divides M. Period. So if you have a prime, then it's settled. Then it divides both M and N, unless the case D equals 2 or D equals 5. So this covers the prime. If D equals 2, what happens here? Well, of course, if D is 2, this doesn't tell you anything, right? But what this tells you is that here, then M and N are both even or both odd. I mean, that's just kind of what you get out of here, because these two things, they to be 0 mod 2, these have to both be even or both be odd. Simple. So that's what I've got so far, right? And what happens if D is 5? Well, if D is 5, well, let's take this case here. If D is 5, and D, that is 5 divides N, and 5 divides M. Divides M. And if D divides N, oh, wait a minute, I got this wrong. If D divides M, right, then D divides M. If D divides N, then D divides N. And if what happens if D is 5 and D divides M, then this equation is automatically satisfied and we don't know anything. However, this case, so I've gotten kind of into a mess here, because the two cases needs to be sorted out, and then we also need to deal with putting these equations back together for products of primes. But let me give you a shortcut here, and that is, we'll come back to this. Really to show that cannot be satisfied for so back here where we did this, the AB thing, when we wrote this out, we haven't come here yet, but we really don't need to do this complicated. We only need to assume A and B are integers, which, as you can see, will greatly simplify the computations there. And the reason is because this is integral over the integers. Everything in here is integral over the integers. So remember what I said about when you take the integral closure of an integrally closed ring, it's the same thing. When we get to this, it will help us sort of simplify this a little bit. Just for fun, see if you can work this out. This does work out because, in fact, so I'll finish the thought on the example, even though we didn't finish the computation, because it's too weeds. We got to do more number theory to it. Maybe 5 is integrally closed. But not a UFD. Because many of you have already kind of seen this example in a previous, like a number theory course, whatever. This is not a UFD, but it is integrally closed. Here's another example. Here's one that I can give us a little bit more concrete. I claim that this ring is integrally closed. The quotient field here is QX. So suppose f of x in QX is infinite over R, where R is not constant. I claim f of x is actually in QX. This is the same trick that I used before. If f of x in here is integral over this, then it's integral over QX. And what ring structure does QX have? It's a PID. So this makes my computation much easier, right? So I don't have to consider quotients of polynomials. I just have to consider polynomials with rational coefficients, which is much easier to do. So suppose now we can assume that f of x is in QX and its integral satisfies f of x to the n plus, let's say, r n minus 1 of x, f of x to the n minus 1, x, f of x plus r0 x 0. Assume it's integral like that. Now, plug in and I get f of 0 then plus rn minus 1, 0, f of 0 plus r1, 0, f of 0 plus r0, 0 is 0. And notice these are all integers, right? And f of 0 is an element of the rational numbers, but Z is integrally closed in Q, So f of 0 is in Z, therefore f of x is in Z plus x QX. So this ring is integrally closed, and it's not even atomic, right? But not UFD or even atomic. As the element X in this ring cannot be factored into irreducibles at all. You might think about, I think I may have mentioned it, or you might think about why this ring is not atomic, that is why it can't be factored into irreducibles, and I'll pick it up there next. Any questions?
Already seen why.
What's that now?
We have already seen why it's not atomic.
Maybe we have. It all runs together in my soup that I call a brain. Okay. Any questions? All right, you guys stay dry, and we will see you on.